question 6. So I think the problem with a question like this is just getting the diagram sorted out. So I've put in all the forces up here with regard to Q. Okay, so we have the tension of 6.4 here. We also have a tension of 6.4 here. Think about it, it's being pulled because this string is going along through here and then up here. We really have a sort of a multiple force. So we have a 6.4 here and a 6.4 here as well. We obviously also have the weight of the particle Q. So let's try and work out the mass of M. So if we resolve vertically, obviously our force going upwards is the this component of the 6.4, the adjacent component. So that's 6.4 cos 40. That's our force going upwards. Our only force going downwards on Q is the weight, so that equals mg. Obviously G is 9.8. This allows us to work out that M is 0.500 kilograms. Now we're being asked to calculate the force H. So if we resolve horizontally, so our forces going to the left, we have this 6.4, the green one, but also the opposite, but this component here of this 6.4, so that's the sin 40, so 6.4 sin 40, that little red arrow there. So our two forces going to the left are this green one and that component of the red one. So there are the forces going to the left. Our only force going to the right is H, allowing us to work out H to be 10.5 newtons. Now for part 3 we're moving over to considering P. So let's start the diagram again. So from the point of view of P, we have that 6.4 going in the opposite direction. We have our normal reaction, we have the friction up the slope, and we have the weight of 32 newtons. So, what are we being asked to do here? Yes, show that yes, we're trying to work out the coefficient of friction. So, let's start off by resolving perpendicular to the plane. We're purely doing this because we need to work out what R is, because R is a component of the friction. Friction equals mu R. So, in a minute, when we're resolving down the slope, we're going to need to know what R is. That's why we start off by resolving perpendicular to the slope. So resolving in this direction, we have the forces going upwards at an angle are R, but also this component here of the 6.4. So that is the 6.4 sin 30. So our two forces going in this direction are this black force here, which is R, and this element of the green force, the 6.4 sin 30. And what have we got going in this direction? Well, it's just this purple force here, this component of the 32 newtons here. That's 32 cos 30. So R is our only unknown. That allows us to work out that R is 24.5. Now, if we now resolve up and down the slope, so resolving in this direction, okay, our only force going up the slope is the friction, which is mu times R. R we've just worked out to being 24.5, and our two components going down the slope are 32 sin 30. That's this purple component here, 32 sin 30, and 6.4 cos 30, this green component here. So this allows us to work out and prove that the coefficient of friction is 0.879. Now for part D, we're now being told that that the 6.4 is the string, Q and the string are now removed. So basically all this green stuff disappears. Okay, so we start again really resolving. So resolving perpendicular, the only force we now have, well R is the only force going in this direction. because obviously this is all gone, but we still have this purple component here, so R equals 32 cos 30. Now our maximum friction is our coefficient of friction times R, so 0.879 times R times 32 cos 30, which is 24.4 newtons. So that's our maximum available friction if we need it. Now the weight down the slope, okay, obviously this green's all gone, so our only force down the slope is this component, this purple component here of the 32 newtons. That's the 32 sin 30, opposite, it's 32 sin 30, that is 16 newtons. So basically the weight is 16 newtons down the slope. We've got up to 24.4 newtons of friction to use, which is plenty to counteract the 16 newtons of weight. Therefore it remains in equilibrium.